when we consider that these are the Galilean variables and the motion variables, these are only useful in a very specific, narrow set of circumstances where the acceleration is constant. If I want a more generic or a more generalized view, then I probably need to consider the derivative relationships. And let's see. Ryan, can you tell me what the derivative relationships are?
V squared equals 2a displacement plus v naught squared.
Nope, that's just another Galileo's motion equation. I'm looking to see what is one of the derivative relationships between the motion variables. Do you know what those are? Let me see. I'll get some help. So, Oliver, do you know what the derivative relationships are? No, I'm looking for one of the derivative relationships. It's a calculus term. So acceleration is the derivative of velocity with respect to time. That's one of the derivative relationships. And so I think once you get one, the other one should be pretty easy. That velocity is the derivative relationship of position with respect to time. So these will work under any circumstance. This works only when the acceleration is constant. And these are the variables that we tend to observe while looking at an object's motion. So this is what we developed when we were talking about kinematics. And yes, there's a total of 5 of these, and you should have access to all 5 of them. At this point, these are considered translational motion. They detail how an object changes location, moves from one place to another. But they're not the only type of motion that exists. I want you to consider this. But we have a set of symbols we're going to use to describe rotational motion, and a lot of the things that we associate with rotational motion will be exactly the same as translational motion. So let's start by talking about the symbology that we're going to use. I'm just going to slide that over there. First, whether I say angular or rotational, they mean the same thing. So if I say angular velocity or rotational velocity, I'm saying the same thing. There's no difference between the two words. And the books and your problems will use them interchangeably. So there is no difference between rotational velocity and angular velocity. Similarly with acceleration, similar with displacement. It's just whatever word they happen to use at that moment. I tend to favor angular in most of the conversation that I have, but there's no real reason for that. So time, as a variable goes, isn't a rotational property, so there's no reason to translate it. A measurement for time is going to be t, whether I'm dealing with rotational motion or translational motion or both. However, for acceleration, we are going to use a different symbol here. And in order to try and be clear about what these symbols look like, I'll give us the kindergarten paper for a minute. I'm going to use, and so does the book, the Greek letter alpha for angular acceleration. It's kind of nice because they're both A. The problem is that I tend to be messy. So when I write alpha, it's going to look something like that. But alpha is a lowercase letter, even in the Greek alphabet. And compared to other letters, it should be half the size of a full-size letter. Does that make sense? So we'll use that symbol for angular acceleration. Now, when it comes to velocity, we're going to use the Greek letter omega. And we're going to use the lowercase version of it. So it's like a W. So maybe a script W or a W with a little bit of flair. It's lowercase. So it should be small enough, again, to exist on half the size there. But it might want to have a little swoop that goes above there. When I write it, this is what it's going to look like. Although this refers to the initial angular velocity, or the final angular velocity, I am very likely just to refer to it as omega, like say sol for omega, in the same way that I might say sol for v. But it is a Greek letter omega. For displacement, though, we're talking about an angle measure. So we're going to use delta theta for displacement. As I talked about before, theta is a lowercase letter, but it is a tall letter. So when you're writing theta compared to omega and alpha, it should have the features of being a taller letter. And the other one should be smaller. Now, I'm not trying to be demeaning. You're going to have to write out equations, and you're going to have to assume that the person that's grading yours can translate what you're trying to mean. If they're telling you that your answer can only have omega, alpha, and theta in it, those symbols have to look similar enough to what the representation is of them. So their sizing is one of the ways in which you can make sure that you are being comparative appropriately when you're writing out these formulas. Now, there are some important distinctions here. In kinematics, we generally used MKS units, but there was no reason we couldn't have used feet or kilometers or miles. We just didn't. I tended to try and keep us from having to add another layer of work to do conversions from one unit to another unit. Angular and rotational is going to pose a bit of a problem there, because there's not really a variety of units like there are with translational motion. With translational motion, meters, feet, it was obvious. We were going to have something that had to deal with length and time. With angles, we tend to measure things in values that aren't necessarily considered units. For example, it's really common for our velocities to be something like RPM. RPM is shorthand for rotations per minute. It's not written as a fraction or as we would normally consider units to be written, but RPM is rotations per minute. RPS, rotations per second. So while they might write out rotations on the top of a fraction and seconds on the bottom, they will more than likely write velocities like this. But we can also have degrees per second or radians per second. The problem here is none of these are actually units in the traditional sense that we consider units. Meters, feet, miles, these were human-made measurements. We just arbitrarily picked some distances and gave them names, but that's not true for a rotation. A rotation has a specific meaning. Similarly, radian isn't a unit. In fact, you've been discussing this probably in your math class. Radians aren't units. You don't have to write out the word radian if you know your angle measure is in radians. For us, in this class, I'm going to strongly encourage you to write out the word radian, or at least put rad if you know that that's going to be your measurement. You don't have to, but it's probably in your best interest to be very clear about what your units are. We will very seldom use degrees in this setting. We will almost always reserve degrees for angle measures in a problem, like the angle of an incline or something like that. We'll very seldom use degrees in rotational motion. Doesn't mean a book problem that I assign doesn't have degrees as a problem. So you need to be familiar. So when it comes to theta, we could have rotations, degrees, or radians, all as the different units of measure, even though none of them are actually units. And I'm of a mind that you guys are pretty aware of how these three things are related. And that one rotation, 360 degrees, 2 pi radians. Now, almost always acceleration is in radians per second squared. Almost always. There's very few circumstances where you get your acceleration in rotations or something like that. They almost always go radians. Now, using these as our kinematic variables, you should be able to translate your Galilean motion equations into rotational motion equations. So find your list of 5 and make short work of translating them right here in your notes. I'll give you 2 or 3 minutes, but I want to come by and see that you've done this correctly. I mean, I'll start you off. Omega equals alpha times t plus omega naught. So generate the other 4. Having done this for years, I have found that for whatever reason, you can tell students that this is no different than stuff they've already done, and they seem to acclimate to it pretty well. When it comes to actually getting to work, students find rotational motion to be somewhat challenging. And I'm not sure where the disconnect is. But right here should be what you guys have written down. I'm just rewriting them for all of you in an effort to ensure that you have all your minuses in the right place and all your squareds in the right place. Make sure that you have them correctly expressed. If you have the 5 regular motion equations correct, there should be no reason why these are incorrect. They are the same. There's no reason to have to memorize 2 different sets of things. The only difference is that where you see angular, you'll have linear. I'm sorry, where you have linear, you'll have angular. That's the only difference. But it also should be clear that when we're dealing with something where the acceleration is not constant, remember acceleration is the rate of change of velocity, or velocity is the rate of change of position. So whether we're dealing with a Galilean style motion or we're dealing with something where the acceleration is more complicated than that, we still have a whole set of kinematics that is largely identical to what we studied back in September. Now, I generally don't spend a lot of time redoing this, but the last couple of years I found that students really struggle with this transition. So how many of you know what a record player is? All right. Standard record players came with 4 different speeds. There was 16 RPM, 33 1/3 RPM, 45 RPM, and 78 RPM. Consider a long play record. Long play record was generally played at 33 1/3 RPM. Let's say it takes 8 rotations for your record player to get your record up to speed. So you put the record on the record player at rest, you turn it on, and in going from 0 to 33 1/3 RPM, the record made 8 rotations. How long did it take for the record player to get the record up to speed? And what was the angular acceleration in radians per second squared? I'll say it all over again, but once I turn you loose, I should be able to call on any one of you. Again, we have a record player, and we're going to spin the record up to speed. The speed that I've chosen is the 33 1/3 RPM. In getting up to speed, the record makes 8 rotations. How long does it take the record to get up to speed? And what is the angular acceleration in radians per second squared? Now, if you don't hear the obvious similarities between this and kinematics first semester, then you're going to need more practice. If you see the obvious similarities, you probably have already begun drafting out a set of motion variables that might help you organize the information I've given you. So give it a try. I want to see how much help I have to provide you. And if you're struggling, I've gone ahead and put the information on the board and tried to organize it. Haven't done much, just put the information down. All right, here's what we decide whether you guys are seeing what I'm seeing or not. I don't know where you want to begin, but I'm going to start with the one for time. And I'm going to recognize that I have 3 pieces of given information, just like before, and I'm looking for an unknown, time. Not knowing the acceleration means I can use a relationship that doesn't have acceleration in it. So I'm going to start with delta theta equals 1/2 omega naught plus omega times t. This should allow me to solve for time. Now, I think a lot of people are rightly concerned that they have to convert things, and you will have to convert things. But this problem, I started out pretty straightforward, without much that you would have to do. Delta theta is 8 rotations. As long as every other unit is in rotations, I don't have to convert it. So I'm going to leave that because I have 1/2, 0 plus 33 1/3. That's in rotations per minute times t. Seems to me that if I work this out, I'm going to get an answer. And my answer will be in minutes. As long as I'm okay with that, there's no reason why I shouldn't proceed. So 16 over 33.3. So it's pretty close to a half, isn't it? Maybe a little less than a half a minute. Give me an idea. What is it? What's the decimal? Point what? 0.4 what? Now this is minutes. If you want it in seconds, then convert it to seconds. It's not too hard to do. Now, the acceleration I wanted in radians per second squared. There's really no way around the fact that I'm going to have to take that 33 1/3 rotations per minute and probably convert it to radians per second. I can attempt to solve for alpha and then convert it at the end, but I think we'll be in better shape if we just put everything in terms of radians. Now, it's your choice, but my experience is that most students do need a little refresher on doing some conversion. So I want to take this value for omega and talk about converting it into radians per second. Most students don't have too much difficulty, but there's always 1 or 2 who just need a bit of a reminder. And I know you're working with, the unit circle in your pre-calc class. And you guys are in calculus, should be way beyond that. But I will always use unit multipliers for converting. So I got to convert the rotations into radians, and I got to convert the minutes into seconds. So I'm looking at probably 2 sets of conversions here. I want radians, and I need to get rid of rotations. I need to remember my conversion fact, 2 pi radians for every 1 rotation. And in a similar fashion, I have minutes, but I want seconds. So again, my conversion fact, that ought to do it. So I'll be multiplying everything across the top by 2 pi and everything on the bottom by 60. Finding the quotient and giving myself my value. This will be in radians per second. Converting the 8 rotations to radians is pretty easy. I just can multiply by 2 pi. You may be tempted to leave these in terms of pi. Don't. Get a decimal. We do not answer any of our work in terms of pi unless it's explicitly stated in the problem. So if your problem is going to involve any kind of rotational value, convert to a decimal. Do not answer in terms of pi. Now, I don't really feel like going through with this problem. My personal belief is that you guys should be able to handle a motion equation problem. But are there any questions up to this point? All right, this is the final piece. When we did this for linear motion, we had to be careful because all 4 of these values were vector values. And because of that, we had to be careful about dealing with direction. This is an area where we need to probably stop for a minute and consider, is there a vector associated with the direction of motion here? And you already know the answer to this. What is a common way of describing the direction that something rotates? Clockwise or counterclockwise? Do you understand why that's insufficient? What direction is this spinning? Not to me, it's not. Or maybe not to you, it's not. Do you understand why clockwise and counterclockwise won't work? What if it's spinning the way it was here? What's clockwise or counterclockwise now? Who's to say? We find that that's too arbitrary. And so in science, the direction that an object spins needs to have a more descriptive way of dealing with its direction of spin. And I'm saying that because this direction of spin, you say clockwise or counterclockwise, really isn't enough to describe it to somebody who's not in the room. Because it could be spun at an even more obtuse angle. And now how would you describe it? So describing direction of spin is handled by something called the right-hand rule. And although we're going to learn a lot about different versions of the right-hand rule, this one is one of the easiest to deal with. Objects that spin have an axis of rotation. I think that's kind of obvious. You can kind of see the axis of rotation here. But objects that spin have an axis of rotation, a point in the middle about the rest of which the object rotates. An axis of rotation. We use the right-hand rule to describe a vector that passes through the axis of rotation. And we use that to describe the direction of rotation. So if you will, take your right hand. And this is called the right-hand rule on purpose. It requires the use of your right hand. So when I catch the person using their left hand for the right-hand rule, I will exploit you for sport, so please be prepared for that. The right-hand rule is purposeful in that it gives us all the same point of reference. This object is rotating upwards. We're going to be interrupted, and I'm sorry.